Okay, good evening, everyone, and welcome to this 9th talk of the Exoplanet course. And today we have with us Dr. Joy Monteiro from IISER Pune. I would now request Dr. Ravi to kindly introduce our speaker for the day.
Okay, hello everyone. Thank you for coming, and we welcome Professor Joy Monteiro from IISER Pune. And Dr. Monteiro is from Earth and Climate Science, and I think he also has a joint appointment from Data Science Department at IISER. And he's an expert in climate modeling, Earth climate system. And today I think he's going to give an excellent background on Earth and solar system planets and their atmospheres. So Joy, whenever you're ready, please go ahead, and I'll mute myself.
Just one instruction.
Yeah, please, Prachi, go ahead.
Just one instruction for the participants. So if you have any questions, you can please unmute yourself and ask at the same, like at whatever point you have questions, you can unmute and ask. Yeah, sorry, Joy, sorry.
Yeah, thanks. Good evening, everyone. Thanks for making it to today's lecture. Even though this is an exoplanets course, so I guess this particular lecture will be, in that sense, somewhat different. But it's always good to have some understanding of Earth and solar system planets. The reason being, they're among the best observed planets. As you may have heard in the previous lectures, observing and characterizing planets away from our solar system is quite a challenge. And therefore, we always try and see what we can learn from the planets that we can observe around us. Hopefully that will also help us understand a little more about planets far away. So I will be mainly focusing on observations of planets, but not trying to give too much information, but trying to sort of build a sort of picture for you on how to think about atmospheres in general, right? So we'll be taking a lot of examples from our own solar system, but the idea is to build that bigger picture, which will help you even when you're not thinking about Earth or the solar system. So let's start with the absolute basics, right? Composition and mass of the solar system planets, not the planets themselves, but their atmospheres. So this is a pretty picture, and what it shows you is, I mean, the huge variety in terms of sizes, colors, and distances from the sun that we see in our own solar system. So even in that sense, it's nice to look at solar system planets, because we have a huge diversity here itself. Not much maybe compared to what you will see elsewhere, but it is still a significant thing. And as you may have heard, or you will hear, a lot of terminology, even in the exoplanet descriptions of planets, comes from some sort of making analogies to solar system planets like hot Jupiters or sub-Neptunes or super-Earths, so on, right? So in that sense, it is a useful exercise. So let's talk about atmospheres that we observe in our solar system. So as you all may know, we define atmospheres as the gaseous part of a planet, which for gas giants is essentially the entire planet itself. And because of its lower mass and density, these tend to be at the outermost parts of the planet, and almost always they are probably the only things that we can observe about a planet. It's especially for planets with some sort of surface, or even otherwise, it's hard to see deep through the atmosphere, right? And atmospheres play a very important role in controlling the climate of a planet, as we will see in this lecture. But let's start off with what kind of atmospheres exist in our solar system, right? So Mercury practically has no atmosphere at all. It has a very thin gaseous envelope, which consists of elements like sodium, potassium, and so on. Venus, on the other hand, has an extremely dense atmosphere, right? It's, in terms of mass, it's almost 100 times the mass of the Earth's atmosphere, and it mainly consists of carbon dioxide. Earth, as we know, is probably the best understood atmosphere, and it consists of primarily nitrogen, carbon dioxide, and a little bit of water vapor, and a little bit of oxygen. And this oxygen, of course, is very interesting. I mean, not just because it's a sign of life, but oxygen is a very reactive gas. It is very unusual to find substantial amounts of oxygen in any atmosphere. Therefore, there must be some way for oxygen to be continuously replenished in any atmosphere, because it will continuously react with other things that exist in the atmosphere, right? And that's why I have put sort of an exclamation mark. Mars, on the other hand, I mean, Venus, Earth and Mars are relatively closer, as you can see, right? Similar kind of planets. Mars is a little smaller. Venus is much similar to Earth in terms of its size. So Mars has a much thinner atmosphere. If Venus was 100 times, this is 1/100th of the mass of Earth. And it's mainly carbon dioxide. That's a mistake. I'm sorry, it's not carbon monoxide, it's carbon dioxide. Jupiter and Saturn, the big gas giants in our solar system, have huge atmospheres, which mainly consists of hydrogen and helium. It's also true of the icy giants. So Uranus and Neptune are classified as icy giants because they tend to have a much larger content of ices, which Jupiter and Saturn don't have, but they also have similar atmospheres. Titan is a moon of Saturn, which is actually something that has caught the interest of a lot of planetary scientists, mainly because we will talk about it, because it has a lot of similarities with Earth's own atmosphere, not in its composition, but the way it behaves, and we'll see how. So Titan has nitrogen and methane as the dominant composition in its atmosphere. So if you go from Mercury, which is the closest and therefore the hottest, all the way to Neptune, which is now the last planet in our solar system, there is changes in what consists of the atmosphere itself, right? So this is a question to the audience. Can you detect a pattern here? Feel free to answer. This is just an informal discussion, right? So what do you think is the pattern you see going from Mercury to Neptune? No answers? Okay. I think the first thing that will sort of become obvious here is that Mercury's atmosphere contains sodium and potassium, right? Sodium and potassium, of course, are very reactive, and you don't find them as metals themselves, but on Earth, they tend to be solids. So clearly, for them to be part of the atmosphere as gases, the temperature is likely to be very high, which we know, right? Mercury is a very warm planet. Oops. And once you go to the cooler and cooler parts of the solar system, so you go from Mercury to Neptune, what you see is that it tends to get hydrogen dominated. There are multiple reasons for this, but one of the reasons why you don't have, for example, too much water in the atmosphere that is observable is simply because it's too cold, right? In the same way that sodium and potassium are unlikely to be found in the atmosphere of Earth because they just condense and become solids. In the same way, carbon dioxide, water, and so on tend to just condense, and therefore it's unlikely you will find them in the atmospheres of the cooler planets. We'll also talk about the fact that why won't you then have hydrogen and helium in the atmospheres here, right? That's an obvious question. Hydrogen and helium are gases in the kind of temperatures you find on Earth, but they are not part of the atmospheres. So both kind of patterns are worth describing, and asking such questions will sort of help you gain an understanding of how atmospheres can form and what composition they have. Right? So we'll use this information to try and understand what would likely influence the composition of atmospheres. So on the one hand, it's important to know where the planet was formed, right? So as the solar system was forming, you would have multiple sort of distances from the early sun, where certain elements or compounds would start freezing, right? So for example, there could be a line where, or a region closer to the sun where it would be water, and away from that line, away from the sun, it would be ice. Similarly, you can find a line for carbon dioxide. If you come closer, you'll likely find a line for maybe iron and sodium and potassium that you have already seen, right? And as you go further and further away, the only substances or chemicals that will likely not condense will be the less reactive or the so-called noble gases. Hydrogen, helium. Well, hydrogen is reactive, but it still has a very low condensation temperature, right, where it freezes or becomes a liquid. Nitrogen is another option, is another example, and so is helium, right? And the biggest planets form in the region where you have enough of solid material, which include ices, right? So Neptune and Uranus, for example, have a lot of ice, whether it is methane ice or water ice. And the smaller planets don't have that available. And therefore, what is potentially part of their atmospheres will depend on what is available as part of the material that is forming these planets. Another main and important factor is the temperature, right? So as you know, hydrogen is a very light gas, and therefore at a given temperature, it will have the highest kinetic energy, right? Or in terms, or rather, highest velocities. And if you have a planet who has smaller mass, then it's easy for hydrogen to reach escape velocities. I presume all of you are familiar with the concept of escape velocity. If not, just to recollect, escape velocities are is that velocity at which, if any object is moving, it will escape the gravitational pull of the Earth, of the planet, right? So hydrogen will be moving the fastest, and therefore you need to have a very large gravitational pull to retain significant amounts of hydrogen or helium in the gaseous envelope. The heavier gases are therefore more likely to dominate atmospheres of the less massive planets like Earth or Venus or even Mars, right? And the closer you are to the host star, the higher will be the temperature, and therefore the more likely that these gases will escape, right? So there is always this tug and pull between how hot the atmosphere is and which is trying to pull gases away simply because of the fact that they will reach escape velocity, and what is the gravitational pull of the planet itself, which is trying to keep these gases closer to the planets themselves. So wherever this balance is reached will determine what kind of gases will remain in the atmosphere versus those that escape. So, like I mentioned, temperature and gravity are two factors that work in opposite directions. When you have a much more, the higher your gravity, the more likely you will have a wider variety of substances, especially the lighter gases in your atmosphere. Another mechanism or process that influences the composition of the atmosphere is exchange of material with the surface. This is more relevant to planets that have a rocky surface or a solid surface. And usually there could be multiple reasons, such as chemical reactions happening on the surface, or the fact that such planets could also have a molten core, which then release, the heat releases gases or enables reactions which release gases from rocks itself. So exchange with the surface is another way in which you can change the composition of the atmosphere. So again, another question, let's which I think is probably more familiar to all of you. Can you think of, or can you give me an example of how the interior of the Earth exchanges or provides gases or changes the composition of Earth's atmosphere? That's right. So in the chat, people have written, right? Volcanoes and earthquakes, and that's correct. You will have, that's the easiest way in which there is a continuous inflow of water vapor and carbon dioxide, especially into the atmosphere. And another process, which is probably more, I would say, it is unusual because we don't know any other planet which has life. But life can dramatically change the composition. And that's the reason why I had put this exclamation mark, right? So people who study Earth and have looked at the composition of the atmosphere of the early Earth have sort of developed lines of evidence which tell us that until roughly 4.5 billion years, there was hardly any oxygen in the atmosphere. So there was water on Earth, on the surface, right? But there was no oxygen in the atmosphere. And the lack of oxygen in the atmosphere allowed, for example, the oceans to have a lot of iron, right? So the oceans were actually red rather than the color that you're more familiar with nowadays. That is simply because there was nothing available to oxidize this iron. And they have noticed that by looking at rocks, that there are certain times when there was hardly any iron present in the rocks, and then all of a sudden there was a huge amount of iron And that transition period is when they speculate that oxygen was produced for the first time on Earth. And this free oxygen, being so reactive as it is, immediately oxidized the available iron in the oceans, and all of it precipitated into the deep oceans, right, which formed rocks, which we now observe. So a whole different kind of chemistry is possible when oxygen is available in the atmosphere, and it dramatically changes the character of the rocks, of the atmosphere. And therefore, even though it's very unusual, but it is something very important to keep in mind when you're thinking about the composition of atmospheres. There's another interesting aspect to the composition of atmospheres, which is the idea of phase change, right? So on the left-hand side, I have a temperature versus pressure plot, which many of you may be familiar with from your basic thermodynamics, even in the 11th and 12th, maybe even 10th, I don't know, right? So the idea of a triple point. So as you well know, so the triple point is that temperature at which all phases or the three phases, solid, liquid, and gaseous phase of any substance remain at equilibrium, right? So if you look at this plot, when you have lower temperatures and or higher pressures, the substance becomes a solid. And when you have lower pressures and higher temperatures, it's a vapor. And when you have relatively higher temperatures as compared to and higher pressures, you would get a liquid. So I wanted to just focus on this lower quadrant of this plot, right? So if the temperatures you experience in an atmosphere are close to the triple point of any substance, then there's a strong likelihood that you will have the existence of multiple phases of that substance, right? So the most familiar and the best example that we have is on Earth, where the temperatures are close to the triple point of water. So we have water vapor in the atmosphere. You also have liquid water in the oceans, on land, as well as in the clouds, right? Clouds are liquid water. And you also have ice, water ice, which you can see in the form of snow that is raining down from the sky. It's available on glaciers and so many other places. So clearly, this idea of a triple point is very important. And in any planet, understanding what substances in the atmosphere are likely to be close to their triple point is an interesting question. So we can take other examples. Another example is that of Mars, right? So Martian temperatures are close to the triple point of carbon dioxide. So not only is Mars's atmosphere mostly carbon dioxide, but it also has a lot of carbon dioxide as a gas in the atmosphere, or rather just solid carbon dioxide as carbon dioxide glaciers, right? You could evaporate that carbon dioxide into the atmosphere, and during winters that carbon dioxide again precipitates back to the surface. So you can have a sort of cycling of some substance between the atmosphere, land, and sometimes if you have a liquid ocean, then the ocean itself. Another very prominent and well-studied example is of Titan, which I had mentioned. So Titan has a lot of methane in its atmosphere. And again, the temperatures are in the range of methane's triple point. So you have methane glaciers, you have methane gas and methane rain on Titan. So the process of or the ability of a planet to cycle some component of its atmosphere through all three phases is generally called a hydrological cycle. Of course, the name comes from Earth because this is where it was observed first. But the term hydrological cycle now is taken to be more general and also refers to say CO2 hydrological cycle or methane hydrological cycle. So that is a quite familiar part of this thermodynamic diagram that we have all seen. Another part of this is this critical point, which is a particular temperature or pressure above which the substance becomes or goes into a different phase, or state of matter, which is a supercritical fluid. So where it is neither a gas nor a liquid. And to be able, these kind of temperatures and pressures are not observed on Earth, for example, though there is evidence that it exists in hydrothermal vents, which some of you may be familiar with, right? However, it is more common in the larger, oh, I'm sorry. I think I stopped my. So is this back online? Can you guys see this?
Yes, we can see the screen.
Thanks. So the larger planets, especially Neptune and Uranus, not only do they have ices, but the temperatures closer to the core are so high and the pressures are so high that these ices actually are no longer solids, but they turn supercritical. So this is another interesting state that an atmosphere can be in. It could potentially even happen on Earth, especially if all the water in the oceans start evaporating. But it's sort of an exotic phase, which is not commonly observed. Right? And one of the main impacts or implications of having a substance which condenses, evaporates, and so on, is the formation of clouds, right? So if somehow using your telescope or some other ways, you can deduce that there are clouds in any particular planet, then you can, with reasonable confidence, say that that planet has some sort of hydrological cycle. Earth, of course, is a very good example, very obvious example. Titan is another one. This is from the Cassini mission, right? And the bright spots that you observe are actually clouds. You see some on the top here, on the top, and in the close to the equator, and even here, right? So clouds are observed, and they play a quite important role in the climate of any planet, which is why I thought it's worth mentioning it here. So that was what you could observe in the atmospheres, but I also thought it would be nice to put in this slide where, since this is going to be a section on habitability, right? So this picture tells you as what is the likelihood of finding complex compounds of carbon or hydrocarbons, depending on the distance from the sun, right? So you get a whole bunch of simple hydrocarbons with a lot of hydrogen, the farther away from the sun you are, or the star. And as you come closer, these compounds, right, they tend to become more complex, and they even undergo aromatization to form aromatic molecules, and they essentially start losing that hydrogen. And clearly there is some sort of sweet spot, right, where you have not lost all your hydrogen. So this is graphite, which is pure carbon. This is amorphous carbon, and this is hydride, some sort of carbon along with a hydrogen atom, some sort of hydride of carbon. So this, for instance, is completely inorganic. Nothing can be done here. And if you go completely to the coldest parts of the solar system, you find organic molecules that were likely formed in the interstellar medium due to the reaction of carbon, hydrogen, and water in the presence of cosmic rays. But somewhere in the middle is a sweet spot where you can have more complex hydrocarbons without going and completely becoming inorganic. So the next question after composition is the mass, right? So from where does a planet acquire an atmosphere? That itself is a question worth asking. So the first way you could do it is simply capture it from what's around you. So you're forming a planet, there is gas that is there, and simply due to your gravitational pull, you capture some of this. This is likely to be important for larger planets because they have a stronger gravitational pull, but it's unlikely to be important for smaller planets like Earth. On the smaller planets, the more likely ways of creating an atmosphere is formation of gases in the process of accretion, which is when the planet is just coming together and getting built, right? The high temperatures that are experienced will release compounds of carbon, hydrogen, and water. And also during tectonics, which we talked about, right? So this is a plot which says you have a lot of meteorites, right, which form the basic material to form rocky planets. And they contain, knowing what they contain, their composition, what kind of atmospheres could you likely have, right? So you could have, for example, pretty massive atmospheres, which are almost entirely dominated by water and CO2. On the other end of the spectrum, you could have very small atmospheres, which are mostly either carbon or hydrogen based, right? Let's ignore this panel for now. But the point is that the starting material that you use to build your planet will likely influence what kind of atmosphere you end up with. And the release of gas during tectonics we have just talked about, right? So that is another way in which you end up building an atmosphere. And a way of losing mass from the atmosphere is atmospheric escape, which again we alluded to initially, which is simply the fact that there is no lid on top of an atmosphere. So your atmosphere essentially fades away into space. And when you have solar wind or charged particles that are incident on your atmosphere, they will likely strip away parts of your atmosphere. And this is the reason why, if you have very strong solar activity or stellar activity, right, you will likely get rid of a lot of your atmosphere. And another way is what we talked about, is the hydrological cycle itself. This on Earth, it does not play a big role, but on Mars, certainly it plays a big role, right? A significant fraction of the atmosphere of Mars actually condenses in the winter and then is re-evaporated. So the mass of the atmosphere itself varies quite a bit between the cold and warm parts of the season, of the year, the Martian year, that is. And if, for instance, you have an atmosphere that is almost entirely steam based, right? Again, if the planet is cool enough, you can likely have a strong impact of the hydrological cycle on the mass of the atmosphere. Right. So, okay. So now we started off with a planet. As the planet was formed, so did the atmosphere form. And due to a variety of factors that we talked about, now this atmosphere has a certain kind of composition, right? And now the question is there anything interesting that this atmosphere will do to influence what happens on the planet in terms of its energy budget or its temperature? Both are the same thing, as we will see, right? So this is a plot which is, actual measurements from satellites on Earth. So on the one hand, you have sunlight, which is has a certain spectrum. This is known as the black body spectrum. And it is emitted from the sun at a particular temperature, which is around 5 to 6,000 Kelvin. Right? And primarily, this emission is in the ultraviolet and visible, and some parts of the infrared. On the other hand, there is also emission from the Earth, because the Earth has a temperature, and any body that has a temperature will emit electromagnetic radiation. And this is much cooler, which is more in line with the temperatures of Earth, because which is between 210 to 310. You will see that it's roughly somewhere in between. So it's around 250, 260 Kelvin. That's where this seems to be. And the second panel tells you how much of the radiation, whether it is coming in from the sun or leaving the Earth, is absorbed or scattered, right? One or the other. And you will see that there are very few parts of this entire spectrum which are actually left without, which have been spared in some sense. There's a lot of absorption happening in the atmosphere. And let's see what causes this absorption. So the biggest culprit is water vapor. As you can see, water vapor practically absorbs everything post 10 micrometers, right? Or slightly after 10 micrometers, maybe around 15 or so, right? There's hardly anything that water vapor will allow. Then there's a huge amount of absorption close to the 10 micrometer band, also due to carbon dioxide. Oxygen and ozone, we know very well that it absorbs UV, ozone especially, and that shows up here. Methane has some absorption in the infrared as well. And Rayleigh scattering itself, which we are familiar with, which causes the colors that we observe in the sky. And that is usually in the higher parts of the spectrum, including blue, right? So there is this one part where we have significant emission from the Earth, and that corresponds to a dip in both the absorption of water vapor and carbon dioxide. And this is known as an atmospheric window. So when you send a satellite to space and you want to look down on Earth and observe some property of the Earth, which is related to its temperature, right? Which means you want to observe infrared radiation. You would want the sensor on that satellite to be sensitive to this particular wavelengths, to these wavelengths, right? In the visible, it's not that much of an issue. There is still sufficient amount of radiation that passes through. But in the infrared, that's not at all the case, right? And therefore, this atmospheric window is critical in allowing surface radiation to reach space. So the question is, why is it that these molecules absorb radiation at all, right? And that brings us to the question of what determines the opacity of the atmosphere, specifically for the Earth, but in general. It has to do with the fact that there are certain energy or modes of rotation and vibration that any molecule can have. Let's start from here. So let's say you have an angular molecule. It can absorb a photon of energy, which allows it to stretch in this way, which is asymmetric or symmetric. It can also twist. It can also bend. And so there's a whole variety of ways in which a molecule can react once it absorbs a certain amount of radiation. And since we know from our 12th onwards that all molecules can only absorb radiation in certain wavelengths. So there we studied it in the context of electron transitions, right? So an electron can only absorb that much energy, which allows it to go to a higher energy state. In the same way, each of these corresponds to certain energy states, and the photons that are absorbed need to be sort of in the particular wavelength that gives it that energy. So this is for a single molecule with a couple of, let's say, a carbon with 2 hydrogens. And this is how it will likely look for more complex molecules, right? So as you can imagine, there will be a wide range wavelengths or photons that any molecule can absorb, which tells you something about carbon dioxide. These are all isolated peaks corresponding to particular rotational or vibrational modes. But water vapor, on the other hand, is very unusual. As you can see, it sort of absorbs all around the spectrum. And especially in infrared, it has a wide, it's what one would call a broadband absorber. And this has to do with the fact that unlike more linear molecules such as CO2, there's a very strong polarity in H2O, which allows it far more degrees of freedom, in the sense that each one of these is a degree of freedom, so to speak. And that allows it to absorb much more in terms of different wavelengths of photons, right? And therefore, you will see that water vapor is a very significant contributor to the opacity of the Earth's atmosphere. And this is in general true for an atmosphere which has water vapor in any planet. And the amount of photons that they absorb or energy that they absorb depends on how many of these molecules there are, right? And that is given by the concentration. So when we typically talk about parts per million, let's say for carbon dioxide, right? In every million molecules of whatever is dry air, there are, say, 300 to 400 molecules of carbon dioxide. And the more the number of carbon dioxide molecules, the more likely that a photon that is emitted from the surface is going to encounter a carbon dioxide molecule, right? And therefore, it is likely to get absorbed. So the more the amount of CO2, the more the photons get absorbed, and therefore the gas or the atmosphere appears opaque. And this is also true for hydrogen, I mean, water vapor or methane, but I'm just taking an example. And in the same way, pressure and temperature allows access to more or less vibrational and rotational states, and therefore changes this so-called absorption spectrum of the atmosphere. So, okay, there is absorption in the atmosphere, but there's also emission, right? And from where is that emission coming from? That's a very important question. And that brings us to the idea of radiating or emission height, right? So this is an interesting plot where you have the emission spectrum of the Earth, right? This is in the, this is the same as this. And on top of it are overlaid different ideal black body spectra. So let's say the surface was close to 300 Kelvin. Clearly, none of the absorption or the emission is coming from the 300 Kelvin range, right? So the surface is really not emitting any photon that is reaching space. On the other hand, the 280 Kelvin or slightly above 280 Kelvin, there is a significant amount of emission which is reaching space. So this is what would be observed by a satellite, let's say 70 kilometers up. And if you look at more or the less energetic or the far infrared, you will see that the temperature from which emission is coming is likely lower, say 260 Kelvin or even 240 Kelvin, right? So since there is some sort of variation of temperature with height, which is shown here. So it's close to 300 at the surface, it goes down all the way to 220 and then increases and then decreases. So it's likely that photons that are emitted in this wavelength are coming somewhere around 260 Kelvin, which is somewhere here, right? Or it could be from here, but it's more likely to be from here. And these are likely to be coming from close to the surface. And the 240 ones are likely to be coming from here, which is almost 10 kilometers above, right? And this plot sort of summarizes how to think about these ideas of emission spectrum and absorption spectrum. So let's say you had an atmosphere which is completely transparent to emission from the surface. A good example is nitrogen. Nitrogen doesn't really absorb much at all, right? So the atmosphere, this is some piece of the atmosphere which is at some temperature, right? So the emission from the surface does not interact with the gas itself and simply escapes to space. And the atmosphere itself has some temperature and therefore it radiates. So, and this radiation is called a back radiation when it is associated with radiation coming back towards the surface. If the atmosphere is slightly absorbing, let's say we go from nitrogen and we add a little bit of carbon dioxide in the atmosphere, then what emission from the surface passes through this? Those photons are absorbed by the CO2, some of them, and a smaller amount escapes to space, right? And the photons absorbed here sort of energize or heat this part of the atmosphere. And therefore, the amount of radiation that it emits will also increase because now it's hotter. The most extreme case is when it is completely opaque. Let's say you put in so much CO2 that practically any photon that's emitted from the surface gets absorbed. Also, be very careful that it will only absorb in this band. This band can become broader. That's a different issue. But there are still photons that are likely to escape, right? So we're only talking about the places of the spectrum where there is absorption. So then nothing escapes to space, and all of that is used to heat up this part of the atmosphere, and that results in that atmosphere itself emitting a fairly high amount of radiation. So now, again, back to question time. Given that higher concentrations of any gas are likely to coincide at regions of high pressure, what do you think, where do you think will be the largest amount of absorption in the atmosphere, going by this plot? So which part of the atmosphere do you think will have the highest pressure? That's likely to be closest to the surface, right? So what do you think would happen in terms of absorption in these lower part of the atmosphere versus upper parts of the atmosphere? Any guesses?
You can type your answers in the chat box or unmute yourselves. So we have one answer. Absorption is more in the lower parts.
So yes, that makes sense, right? So the pressure is high, which means there are a lot more molecules in the lower parts of the atmosphere, which means there is also a lot more carbon dioxide, for example, in that part, which means all the emission from the surface is more or less getting absorbed. And that's exactly what this is telling us, right? That even though the surface is closer to 300 Kelvin, most of it really doesn't get seen in space at all. So this also means that quite likely the lower parts of the atmosphere, which are more opaque as compared to the higher parts of the atmosphere, which are more transparent, this can be transparent simply because it has less molecules, right? So you transition from something that's opaque to absorbing to transparent. And these will likely be the hottest parts of the atmosphere, and these will likely be the cool parts of the atmosphere. And while this is what you see in gases, but you also have clouds, right? So clouds are simply droplets of liquid which are suspended in the air. So if you can think of them simply as sort of putting a lot of mirrors, very, very small mirrors in an atmosphere. And for that particular reason, they're very good reflectors of light, especially the light that's coming in from the star. On the other hand, they're also very good absorbers in the long wave, which is the emission from the surface. So they reflect a lot of sunlight, but they absorb a lot of radiation that's emitted from the surface, right? So again, a question. If you have a cloud lower, would it have more cloud droplets than if a cloud was higher in the atmosphere? What's your guess? I'm seeing the chat, so I will see if you type something. So you can also think of cloud droplets as parts per million, right? So if you have a few hundred parts per million or particles per million, where would you have more cloud droplets? Nearer to the surface or away from the surface? Yes, that's right. So now you have more cloud droplets closer to the surface, then what do you think will be the reflectivity of these clouds? Will low clouds reflect more or will high clouds reflect more? So think of it as having a lot of mirrors, right? Exactly. So you have a lot more droplets. Therefore, it's like having way more mirrors. And therefore, the lower clouds are extremely reflective as compared to higher clouds. But they're both very good absorbers, right? And therefore, the higher clouds tend to trap more heat rather than low clouds. So low clouds tend to reflect away energy from the planet, whereas high clouds tend to trap energy in a planet. And this is the way that clouds can affect the amount of energy that is transmitted via radiation between the planet and space. So this brings us to the next big question, right? So, okay, now you have all this radiation that's being emitted from the surface. There's also radiation coming in from the star. We are going to focus on the situation where geothermal heat is not so much, which is a reasonable assumption for rocky planets, maybe not so reasonable for other planets, but we'll just use that as an example. So, like we talked about, the lower parts of the atmosphere are going to get really, really hot as compared to the upper parts of the atmosphere when you have energy being exchanged in the form of radiation. But when you think about it, it's like boiling a pot of water, right? So you're really heating the bottom parts while not so much heating the top parts. So there is likely to be sort of overturning. The heavier, denser air or gases will sink, and the lighter, hotter gases closer to the surface will start moving upwards. And this process is called convection. And this convection occurs as long as this unstable situation remains, right? So it's a process of restabilization, right? And it happens very fast. Radiation usually takes a longer time to heat or cool, whereas convection can redistribute energy very quickly and restabilize the atmosphere. Therefore, you have, when you get a stable profile, this is the kind of temperatures you observe, right? Forget about all this terminology, it's not very important. But you would probably have a much steeper temperature reduction if only radiation was playing a role. But convection makes it a little less steep, and you get this sort of I'm sure you would have heard of these numbers somewhere or the other, right? Decrease of temperature with height. This is known as the lapse rate. So on Earth, because we have water vapor which will condense, the lapse rates observed are very close to 4 to 6 kilometers. But if you had an atmosphere where there was no substance which can condense, you will have a much steeper reduction in temperature with height. So this convection where no phase change occurs is known as dry convection. And if phase change also occurs, why would phase change occur? So let's say you have a very hot gas close to the surface where also evaporation is taking place, and that air moves upwards where it becomes cooler. Then simply because it's cooling down, there is going to be condensation. And when condensation occurs, it's a completely different way in which convection is happening as compared to when no condensation occurs. Therefore, you have the dry convection and the moist convection. And the interaction between radiation and convection, which sets the vertical structure of temperature in an atmosphere, that's known as radiative convective temperature profiles, right? So you will see this in all planets in the solar system, and this is generally true for any planet, that when radiation and convection are both active, you will see a reduction in temperature up to some point, and after which you can either become roughly isothermal, or you can have an increase in temperature, right? Certain planets, the increase is more dramatic, whereas in some others it is not so dramatic. Venus is sort of an oddball, where the temperature actually cools further with height after that place where there's a slight isothermal layer, and then it begins to cool. But the idea here is that you have such a wide variety of planets, but the principles that govern the way the vertical structure of temperature occurs is very similar, which is radiation and convection acting in tandem, right? And this optical depth is a measure of opacity. And what this is telling you is that there is some depth, some opacity, until where radiation and convection both are active, right? And once you reach a sufficiently low optical depth, all the radiation escapes to space, which is what we talked about here, right? So you have this opaque layer at the bottom, absorbing layer in between, and transparent layer here. So most of the emission from the surface is absorbed by this opaque layer, and this opaque layer then radiates. That, let's say, is partially absorbed by the second layer, and a little bit is emitted from it, which is then goes to the transparent layer, and all of it goes through, right? So this is sort of some depth or some height at which all the radiation that is incident is more or less escaping to space. And that part of the atmosphere where below that level is known as the troposphere. And that level itself is usually called the tropopause, though these two are not necessarily the same thing. But it's also called the emission height, which we talked about. And those parts of the atmosphere above are known as stratosphere. So the stratosphere can have an increase in temperature, as we talked about, but it could also be fairly isothermal. So for example, the Martian stratosphere is mostly isothermal. And you will have an inversion, or rather an increase with temperature with height, when the shortwave absorption is very strong here. So for example, on Earth, because of ozone, there is strong absorption of ultraviolet, which is why you get this sort of an increase with height. And similarly, other gases can do similar function in other planets, right? So all these concepts together help us understand what is known as the greenhouse effect. So let's say you had lower amount of greenhouse gases, right? Which is the first case. So the temperature at which the radiation escapes to space is roughly constant. Why that is so, Jacob will probably talk about it tomorrow. But that is simply because it is dependent on how much energy is coming in. So let's take this particular height at which the greenhouse gas concentration is low enough that all photons escape to space, right? Here. And that temperature is also the emission temperature of the planet. And you have a lapse rate, which is what we talked about here. Let's say it is, for example, 9.8 Kelvin per kilometer. So you are coming down at 9.8 Kelvin per kilometer, and then you hit the surface, and that is your surface temperature. Now, let's say you had higher greenhouse gases. Now, clearly now the concentration of CO2 at this level is more. Therefore, photons from here will not go to space. So you have to go much higher into the atmosphere so that the amount of CO2 or any other greenhouse gas is sufficiently less. And from here now, the planet is radiating to space, right? Now, again, the temperature here and here have to be the same. Like I said, you will talk about it tomorrow, which is known as the emission temperature. But now see what happens. The temperature here and here may be the same, but now you have to come down along that 9.8 Kelvin per kilometer and reach the surface. So now suddenly the surface temperature has become higher, even though you had the same emission temperature, simply because the level or emission height has increased. And this impact of changing greenhouse gas concentrations on surface temperatures is known as the greenhouse effect. So usually the greenhouse effect is explained as some sort of blanket and trapping of more energy and so on and so forth. But this is the correct way to think about what is the greenhouse effect. So now let's look at some examples from our own solar system, right? So this is the amount of energy from the sun that each of these planets receive, right? And this is their reflectivity, or what is known as albedo. Now, these are what are the predicted temperatures for these planets based on how much energy they receive, right? So if you look at Mercury, the predicted temperature, and this is what is observed. So the predicted temperature and the observed temperatures are very close, right? And the reason for this, like I mentioned early on, that Mercury literally does not have an atmosphere. Therefore, whatever radiation you're observing, it's as if you went here, took this level and put it right at the surface. Which is why the predicted temperature and observed temperature are very close. Look at Venus, for example. You're expecting 232 Kelvin, but the observed temperature is incredibly high, right? Which likely means that the greenhouse effect is extremely strong on Venus. Earth also has a moderate greenhouse effect, right? It increases the temperature by here, I think 30 or so Kelvin, which makes Earth have a very comfortable surface temperature. If you go to Mars, like I mentioned, it has a very small or light atmosphere. So these two are much closer as compared to Earth or Venus. And certainly it's not just 3 Kelvin, it's more than that, which shows that there is some sort of greenhouse effect, but it's clearly not sufficient to make Mars have a nice, comfortable surface temperature. Is there a way to independently measure or estimate albedo? Right. So yes, the way it is conventionally done for Earth is, and I'm sure through Ravi could pitch in here, I don't know how they would do it in using telescopes, but the idea is simple, that you just sit on top of the planet and see how much of the energy in the short wave, or the which is in the UV visible and so on, is observed. And then you also measure how much is coming in. Both of these are relatively easy to measure once you are in space, right? And therefore you can actually get a good estimate of what is the albedo. So now going back to the more general case, right? So like I mentioned, that there is a reduction in temperature with height up to the tropopause. And this allows you to have different cloud decks, right? So clearly different substances condense at different temperatures. And let's say you have a span, for example, in Saturn or even in Jupiter, where you're spanning the triple points of a lot of substances. So you can have multiple decks of clouds, which are made of different materials, different substances, I'm sorry, right? And to have clouds, you need something that was gaseous, that was moved up, which then condenses. And water condenses quickly. Ammonium hydrosulfide does not, which continues to be a gas, which is again pushed upwards, and then it condenses. And ammonia is not yet condensing. It's a gas, it moves up and then it condenses. So the appearance of clouds not only tells you that there are condensables, but it also gives you an idea of the weather of the planet and the existence of a troposphere. So like we talked about, there's a troposphere which is being mixed all the time, right? Because on the one hand, radiation is trying to heat the surface, making it unstable, and convection is trying to stabilize it by moving all that hot air upwards. So this part of the atmosphere is continuously mixed. Hence the name weather layer. The stratosphere, on the other hand, there is no such instability. So it is calm and stable, which is why people would have told you that's the reason why planes fly there, right? Because it doesn't experience the sort of dramatic weather that the troposphere experiences. And that gives you, and the tropopause is the sort of the region which is transitioning between the two. And this is a nice observational picture. I don't know how clear it is on Zoom, but I hope when I share the slides, you can look at them. So you have an orange-ish troposphere with some black tiny specks here, which are clouds, on top of which is a bluish stratosphere, and on top of which is a orange mesosphere, and on top of which is the aurora. Right, so this is a really amazing picture of the various layers of the atmosphere just illuminated by the sun. Great. So in the next few minutes, we'll do a much more detailed look at, we'll have a detailed look at Earth and how all the ideas that we used play out, right? So this is a very famous picture. There are multiple sources for it. This one is by NASA. So it talks about how much of this energy that's coming in from the sun is absorbed by the atmosphere, absorbed to the surface. Some of it is reflected back. And what happens to that energy, right? So if you look at it, the amount absorbed by the surface, the sunlight is 163. But what's emitted by the surface is 398. And this is because there is this huge back radiation by the atmosphere in the presence of greenhouse gases. So the surface has to actually emit far more than the incoming sunlight. Eventually, it all balances out at the top, right? So 340 in will also be equal to 340 out. But within the atmosphere, there is a lot more going on. So there is emission from the surface, which is absorbed by the atmosphere. Some of it escapes to space through the atmospheric window that we talked about. Some of it is radiated back because of the atmosphere getting heated. And there's also an exchange between the surface and the atmosphere, which is in the form of evaporation, transpiration by the plants, and also simply conduction and convection, which is not involving any phase change, right? So understanding this sort of a picture, or being able to make this picture, took a lot of effort and a lot of input from a lot of satellites and other analysis needed to happen. So even though we started observing Earth from satellites from the late 70s, this picture was only made in the late 90s. It took us 20 years to come up with this. But now we can routinely make such pictures, right? And this is a picture of the short wave that's absorbed at the surface and the long wave that's emitted from the surface. Both color bars are the same, so that will help easy comparison. But I only wanted to look at the large picture rather than the finer details. There's a lot of detail here, which is very interesting. But the large picture is that there's a huge amount of radiation being incoming, solar radiation absorbed in the close to the equator or the tropics. Not so much near the poles. This is a mean over 10 years of data. And the change is quite drastic. So it goes from 330 plus here to 30 here, right? So 300 watts per meter squared is the difference between what is absorbed here versus what's absorbed here. But if you look at the emission from the surface, it's actually, if you look at the colors, they're not as spread out as this. They're all in this roughly in this region. So somehow, even though there is a lot more absorbed in the tropics, it doesn't emit so much. Whereas even though there's really low amounts being absorbed in the poles, it emits far more, right? So the sort of fundamental puzzle in understanding Earth's climate is, how can this be a stable situation for 10 years? Clearly, if you're absorbing more than you're emitting, this part must continuously heat up. Whereas if you're emitting more than you're absorbing, this must continuously cool down. So in some sense, the oceans here must evaporate, whereas everything in the Arctic and Antarctic must completely freeze out, even the oceans, right? But obviously that doesn't happen. And that's what we want to explain. And this is essentially the same plot. All I did was subtract these two, and then take an average across all longitudes, right? That's called zonal mean. So you see that there's a net surplus of energy within the tropics and a net deficit of energy near the poles, right? So the big question is, how do you balance this sort of surplus? So clearly you need to move some of this stuff here, this energy. And that is the function of the climate system. So what would happen if there was no atmosphere, right? That's the first question you would ask. So look at the moon, for example. This is how the moon looks during noon, local noon, and local midnight. So the local noon temperatures are a fairly uncomfortable 400 Kelvin. And the midnight temperatures are an equally uncomfortable 100 Kelvin, right? So going from day to night, there's a huge change in the temperatures at the surface. And this is because there is no atmosphere, right? So all the sunlight that's here, incident, heats the surface. And in the night, because there is no concept of back radiation or transport of heat, all of it just gets radiated back to space. Here's a question for you. Can you use this sort of a concept to think about how would the climate of Mumbai versus Pune, or the day-night temperatures in Mumbai and Pune, how would they differ? For those of you who are not from Mumbai and Pune, Mumbai has a much more humid atmosphere, right? Pune has a very dry atmosphere overall. So what do you think will be the day and night variations in temperature in Mumbai versus Pune? Which do you think will have a higher day to night range? You can just guess and then tell me why. Why do you think Pune will have a bigger range? Oh. Yes, basically the atmosphere is transparent and therefore it loses heat more easily. Looks like I'm running out of time. Actually, I've already crossed the time. So I'll try and wrap up soon. So that essentially the same idea, but applied from equator to pole, tells you how much energy the climate system has to transport. This transport is done by both atmosphere and oceans, right? And in the process of transporting that energy from equator to poles, you have the circulation that you're very familiar with somewhere or the other, the Ferrel cell, the Hadley cell, and so on and so forth. And just like just how you would have these vertical movement of air, so you will also have clouds, right? Deeper clouds close to the places where there is ascent of air, and shallower clouds where there's descent. And that shows up in the rainfall as well. So you have highest rainfall close to the equator. I am not going to go into this, but it's something very interesting. Titan also has a Hadley cell, but very interestingly, the rainfall is highest close to the poles. The tropical part of Titan is actually a desert, whereas all the methane that forms its hydrological cycle is close to the poles. Right, and this sort of in the presence of rocks and the surface, this also allows you to, have weathering of rocks, which can then take CO2 and bury it in the deep ocean. Whereas from the ocean, it can also come out in the form of volcanoes. And I'll ignore that. We'll just sort of summarize or conclude with this slide, where we see that temperatures on the Earth, which is the red one, have been very closely in sync with changes in CO2, right? So the opacity of the atmosphere plays a fundamental role in controlling the climate of Earth. And that's the reason why this idea of understanding the role of the atmosphere in climate has been taken from Earth and applied to other planets as well. So yeah, just a quick summary that on the one hand, you need to know how an atmosphere is formed, what it contains, and how massive it can be. Is there a question? And it's knowing its composition and the kind of temperatures you experience tells you something about what can condense out of a atmosphere or not. And condensation, like we saw, cannot change the temperature structure by changing the lapse rate, and it can also form clouds, right, which can dramatically change whether how much of sunlight is absorbed and how much of radiation from the surface is lost. And radiation and convection together play a fundamental role in setting the vertical structure of temperature in an atmosphere, and the opacity and therefore the level from which radiation is emitted to space is the key point to understand what is the amount of greenhouse effect that an atmosphere is providing to the planet. So the more opaque an atmosphere, the higher the emission height, and then you follow the lapse rate down to the surface, you'll have a much warmer surface. So yes, I'll stop here for now. And if you have any quick questions, I'm happy to answer.
Yeah, thank you so much, Dr. Joy. So I'm just looking for questions. So people, if you have questions, please unmute yourself and ask.
Hello.
Yeah.
Hello.
Yeah. Hi.
Hi. Can you hear me?
Yes.
So my question was, it's kind of fundamental. How do we know that planets, apart from Earth, can have a similar structure of the atmosphere, like troposphere, stratosphere, mesosphere, and so on?
Mm-hmm. So this comes from the basic physical principles of radiation and convection, right? So what we said was, if you ever encounter a situation where you're heating the atmosphere from below, then you're going to be in a situation where you're going to destabilize the atmosphere because you're heating it below, which means that lighter gases or the density decreases and therefore it rises up. And the minute you have this sort of instability, you're going to start mixing the atmosphere in that region where there's instability. And when you have an opaque atmosphere or an atmosphere that's opaque to radiation emitted from the interior of the planet, this is always going to happen, which is why we saw when we saw the vertical temperature structures of many solar system planets, right? That all of them followed the same pattern. So that ensures that you have something like a troposphere, right? Next, you come to the place where you're talking about the stratosphere. So stratosphere is simply that layer above which is mostly transparent to radiation, and therefore nothing really is heating it from below. On the other hand, if it absorbs sunlight, like for example, because there is ozone or some other similar gas, then it's getting heated from the top. So you will have sort of a very stable structure. Even if the temperature is constant, it is stable. Why, I will not go into right now. But even if the temperature increases with height, it is very stable. So you will have a troposphere and a stratosphere. Again, the mesosphere is also very common. And the reason simply being that it becomes easier and easier to emit to space as you go closer and closer to the edge of space, right? So because of these basic ideas, you expect practically any planet to have a troposphere, a stratosphere, mesosphere. Does that clarify your question?
Okay. So, any more questions? Maybe we can. Megha Mishra, we can see your hand up. We can take one last question, maybe. In the
Ma'am,
interest of time.
I have two questions.
Okay, yeah, please.
So, like, when you talked about the fact that, like, 4.2 billion years back, the kind of atmosphere that existed on Earth, and the fact that there wasn't any oxygen or considerable amount of oxygen. So, if we have like the current predicting models, and we look at a planet that is identical to Earth, how much certain would we be that in the later stages it might have the same atmosphere as Earth right now?
So I don't think we still understand or we have predictive models for the emergence of life. So that's essentially what your question is asking, right? So if we have to go to a place from a completely primitive atmosphere to Earth-like atmospheres, which means oxygen-rich atmospheres.
Yeah.
You need life. So
no, so like given the models that we have today, and we say existed like 4.2 billion years back, how much certainty we would have predicted that oxygen is going to exist in the atmosphere?
I would say maybe Ravi can correct me, but I don't think we have any confidence in that kind of a prediction at all. Simply because, like I said, Earth-like atmospheres means
life has to play a major role.
Needs to be there. Yeah.
So Megha, are you asking about the Earth atmosphere or exoplanet atmospheres?
Sir, I'm asking, like, if we look at a planet like Earth and we look at its evolution, and if we and the way that like oxygen came into existence, if we were to look at an exoplanet that had the same atmosphere as Earth had 4.2 billion years back, and it was an identical planet to Earth, how much certain we would be that in the future it could be an Earth-like atmosphere as it is now?
So Joy is correct that it is very hard to predict that kind of a planetary evolution. Venus started probably like ours, but we, look at what happened to it because of the probably runaway greenhouse.
Okay.
So it is not a surety or even likely. We don't know the probability whether it will turn out or not. It's completely random.
Okay, sir. And one more question. You said that life plays a major role in the way that like atmosphere comes about existence in a planet. So if we look at like other planets and we study their atmosphere and we are able to like, can we say like what a nitrogen based life would look like, and then study that planet and maybe check out the other parameters that could lead to life, that could lead to the atmosphere in that planet, and then like the remaining part, if we don't have an answer, we could attribute that to the fact that there is in fact some life that is intrinsic to the atmosphere of that planet.
Right. So I guess Ravi is the best person to answer that question because, and I think you will have a few lectures on that, identifying biosignatures and Ravi?
Yes. So are you asking how do we know the nitrogen atmosphere and nitrogen life could be detected?
Yes, like we could say that if a nitrogen based life existed, we would see certain properties in the atmosphere, and then we could check that and maybe make a prediction that it does exist.
So we know the biochemistry of Earth based on the life we have here, which includes not just nitrogen chemistry, but includes other kinds of chemistry as well, including hydrocarbons and that's the methane and water cycle. If you are asking about pure nitrogen kind of life, we don't know how a nitrogen based pure nitrogen based biochemistry works. However, if we want to do our own kind of life detection on another planet, if we know only a little bit of the composition of the planet, including nitrogen, we still are not going to be able to make a definitive conclusion because it depends on the context of the environment the planet is in. How much radiation the planet, the star is, giving to the planet, what is the size of the planet, what other gases could produce these, what other processes could produce these gases abiotically. So there could be false positive. So we need a lot of other kind of information, like Joy mentioned, the flux or how much the planet is emitting out. So that is a very critical thing to know.
So yes, like there were 5 ways it was talked about that we can detect like the atmosphere exists in a specific planet. And if we look at the first 4 that are not dependent on life, they would not we would be very sure that this can be attributed to these 4 parameters. And if there is a slight change from what we predicted, could we then say that it is indicating that there might be life? Like an unaccounted parameter could be life.
Yeah. So until we can rule out with a high confidence every other abiotic processes and natural processes, we should be very careful in claiming that it could be coming from life. We should first rule out other processes that are not produced by biology.
Okay, thank you.
Okay. Vandana, thank you for patiently waiting. Are you still there?
Good evening. Am I audible? Actually, I'm having a moment. I'm not too sure whether my voice is clear or not. Can I speak?
Yeah. Please speak.
Yeah, I just want to ask that this is a critical issue to know that how much away we are from the runaway greenhouse effect. And as the amount of carbon dioxide is increasing and other gases is increasing on Earth, there will be, I think, catastrophic effects when there is a thawing of permafrost, because a lot of fossils are already embedded there and that will be thawed. And also if the glaciers are melting, and all the data of Earth sciences is showing that the rate is quite say fast. So is it be estimated that how much away we are from the runaway greenhouse effect, and which kind of simulations can be used for that?
Right. So it is possible to do such a calculation. Fortunately, planets, at least Earth, from what I understand from the current state of affairs, we are unlikely to push it into a runaway greenhouse anytime soon. You need a significant increase in the amount of energy that the planet is receiving, which means the Earth will run away more in line with how the sun evolves, rather than what we are going to do. The reason being, it's something that I skipped in between, that the planet's circulation can sort of reorganize to efficiently radiate more energy, and that does happen, right? So I would say not anytime soon. Yeah.
Joy, can I just add a little bit to that?
Sure.
Yeah.
That is actually good, but in case this methane is 20 times more potent than carbon dioxide, and that is all embedded in the remains of the fossils. And if that happens, I think can be predictable. That will be, I think, then things will happen at a very exaggerated rate. And won't it be like there should be some modeling done on that how much that predictability can be done or not?
Yes, it is being done. So one of the reasons why people say that CO2 is the main driver of climate change is because it's a very long-lived gas, unlike methane. So methane, you can release a lot of it, but very quickly it gets oxidized. And therefore, the impacts of methane can be very large for a short duration of time. But what you need to, for example, start evaporating the oceans is a very sustained long-term increase of energy, which only CO2 can do. Or the other option is to increase the brightness of the sun, right? Ravi, you wanted to add something?
Yeah. I think you literally answered what I was going to say. That's right. And because both CO2 and the increase in brightness, a sustained amount of CO2 and the increase in the brightness of the sun could potentially increase the water vapor amount in the atmosphere. Eventually, due to solar evolution, we will be pushed into runaway greenhouse. It will happen, but not in the time scales that we can do anything about it. That's what Joy, I think, was saying, if I understand correctly, right, Joy?
Yeah.
So, and the other thing is, we don't have to push ourselves into runaway greenhouse to see detrimental effects to our own population, human population, even well before that. Even if we increase by a few degrees or so, we will reach a temperature where we will not be able to sustain the increase in the temperature. It's called the wet bulb temperature, I believe, Joy, right? So,
right.
Yes, that will be really hard for us to do, where we won't be able to sweat anymore, and then it'll be bad. Well before runaway greenhouse.
There are a couple of other raised hands. Maybe we can take those. And
anyone else? I think those are the earlier ones.
Okay.
Megha, did you?
Megha?
Sir, I have one more question, but it's like slightly not related to the talk, but I've never talked to a climate scientist, so that's why I want to ask.
Yeah, please.
So like there has been a lot of conversation about climate
Megha,
change.
can you just give me a moment?
Yes, sir.
I will be back. Sorry about that. Please tell me.
Yes, sir. So like there has been a lot of conversation about climate change and how that is not a good thing that is happening to the planet and you and us as human beings. But there have been like a couple of scientists that have said like that it's not that significant and it's not a matter that we should look into. So what is your take on the significance or like the gravity of the situation concerning climate change?
Yeah, so I mean, one way to answer that is it depends on who you are, right? So clearly, changes in climate are already, I mean, forget about will, are already affecting the most vulnerable, the poor, the old, the disabled, and so on. And a lot of times when people say it's not significant,
Yes, sir.
they usually are talking from a very different perspective. So most of the some of the people whom I have met who have held similar views have sometimes tended to be geologists, right? So geologists look at evolution of Earth over millions of years.
Yes, sir.
And they know that temperatures have been way higher than what they have been now. And therefore they say, what's the big deal? So we are not doing anything remotely that big. But that doesn't take into consideration the fact that humans have evolved in a very particular climate, and we have organized our society and our civilization with the assumption that the climate is a certain kind, even though it may not be very obvious. But if you start thinking about what all you take for granted, very often it's a lot of it is related to temperature, rainfall, and so on and so forth. So we have organized ourselves in a way that makes us very vulnerable to changes in these quantities like temperature and precipitation.
Yes, sir.
So that is really what is causing the problem. So if we had designed our societies to be very climate resilient from the beginning, then one could always argue that, okay, maybe climate change, yeah, whatever. But we are certainly not in a position to make that claim anymore.
Yes, so like there are people that would say that what Greta Thunberg does is way too extremist. Like it's a pretty pointless stand to take. So do you think that is true?
Yeah. So Ravi had a comment. I'll go back to the slide. So if you look at this slide, right? This is the past 500,000 years, so 500,000 years of evolution of CO2. And if you look at the variations in the present, it's literally a straight line.
Yes, sir.
You see this shaded gray. So the change that we have brought to the climate system in the recent past is something unprecedented over the past million years or so. And that's something that needs to be really taken care of. Ravi?
Yes, I everything you said, Joy. The one thing I wanted, that's what I was asking you to show this one. Look at this plot and see what is so unusual about it. The first thing we will notice the straight line, right? And of course, we'll see those periodic peaks. But then the next immediate thing we notice is absolute straight line that's going up.
Yes,
and, right. So this is not a small change. And it is nowhere close to what the Earth has been doing for whatever number of years. And the comment that people you said people were making, it's pretty small and all. Well, for and Joy again did said the right things. On a geological time scale, for Earth it doesn't matter. because Earth has gone through even worse things than this on changing the CO2 amounts. Even 55 million years ago, or 100 million years ago, there were even changes in CO2 that were even more drastic. However, at those times, humans weren't there. And
Yes.
the reason for concern right now, Joy rightly pointed out, is that we humans are going to get affected. Earth will be fine. Earth has gone through several worse things than like this before. But it's on us, and it will affect us. And that's why it is more important. And you can look at this plot and figure and see how unusual and completely out of I would say balance our system is right now compared to the last 500,000 years. This is not normal.
Yes.
Yeah.
Yeah. Thank you so much.
Okay. So thank you so much, Dr. Joy. Nice to see so much of, good interactions happening over the platform. So thank you so much for the wonderful session. Ravi, would you like to add anything?
No, I just want to thank Joy for this super wonderful talk and the kind of interaction we have. Again, Joy, really, thank you very much for taking the time to do this. And
Pleasure, Ravi. Thanks for inviting me, both Prachi and Ravi.
Thank you for having this. So Prachi, you want to?
Yeah, I shall close the meeting.
All right.
Okay, thank you.
Thanks.
See you all soon.
See you all tomorrow. Yeah.
Oh, tomorrow we will be meeting at 5:30, right? Not at
Yes. Yes, tomorrow we'll be meeting at 5:30. We will also put the message on the WhatsApp groups.
Okay, good. Thank you.
Okay, thank you. Bye.
Yeah, bye-bye.
Bye.